Hello, my name is Keshav Kasturi Rangan, and it is a privilege to present my talk titled Modeling Error in Advanced Control and Thoughts on the Impacts of Modeling Error on Optimization Based Materials Design. This is a consolidation of research worked on by Henrique Oyama and myself under the guidance of Dr. Helen Durand. The advancement of engineering capabilities are often tied to the materials used. It can be difficult to identify the right material that can make an engineering concept a reality. Traditional material requirements include focus on properties of a material, such as meeting a requirement to withstand a certain load, while next generation materials demand additional dynamic requirements, such as the requirement of a material to respond to its environment in a certain manner. Traditionally, materials development has relied heavily on experimentation or the experience of individuals, which can be a slow process and creates a need for faster methods such as computationally predicted materials. There are not currently general computational methods for developing materials. The above mentioned computational approaches include artificial intelligence techniques and optimization based approaches that predict the optimal structure of a material. A major challenge with finding optimal materials, irrespective of class or type, is the development of computationally tractable techniques. Formulating a general optimization-based materials design problem can be challenging as it requires the selection of decision variables, objective functions, constraints, and material property models. If the material model is determined using density functional theory or DFT, then the number of constituent atomic species of the molecule represent the decision variables. Objective function can be represented in terms of ground state energy, and the constraints include the molecular model obtained from DFT and all allowable atomic combinations based on the number of valence electrons. As illustrated earlier, if the optimization based materials design algorithm utilizes a molecular model based on DFT, then the ground state energies of molecules can be determined. However, there are potential challenges that we see with using this method, such as first, computational tractability, second, the solution obtained may not be highly accurate as molecular inputs require experimental validation, which may not be available, especially while dealing with new materials. Other reasons for inaccuracies include insufficient K points or inaccurate Bravais lattice specifications or pseudopotentials. Despite these model inaccuracies, a material predicted by an optimization based materials design algorithm solution should be robust, or in other words, have the expected properties in practice. Robustness should drive model selection and optimization based materials design formulation. Robustness in optimization based techniques has been a topic of interest in various areas of process systems engineering, and it would be expected that techniques for handling different concepts of robustness could, in the future, inspire ideas for formulating an optimization based materials design technique. Our group generally focuses on chemical process control, where robustness is a concern with respect to stability. Though this is different than the issues that would be faced in robustness with an optimization based materials design algorithm, the remainder of this talk will focus on several issues related to robustness in advanced control that our group has recently worked on. The control theory that we will take advantage of in this presentation is an advanced control formulation known as Lyapunov-based economic model predictive control, or LEMPC. This is a model predictive controller that explicitly optimizes economic performance and incorporates Lyapunov-based stability constraints. Now that we know the control strategy to be implemented, there are a few assumptions that we make about the class of systems that we will be dealing with. We consider a class of nonlinear systems with bounded disturbances and bounded inputs. The subscript I represents the change in dynamics of the real process. We consider that the origin of this system is stabilizable in the sense that there exists an explicit stabilizing control law h of x that can render the origin of the system asymptotically stable in the absence of disturbances. The system is stable in the sense that there exists a strict Lyapunov function v for which the time derivative along the closed loop state trajectories under the controller h of x is negative definite for all x in the neighborhood d of the origin. We define omega rho I as a level set of the Lyapunov function in D as the stability region where the state constraints are met. The same assumptions as discussed in the previous slide are made on the empirical models. The change in the dynamics of the real process are captured by the empirical model and represented by the subscript q. We define omega rho safe q as the level set of the Lyapunov function, in D as the stability region where the state constraints are met. We define an additional region omega rho q within omega rho safe q to account for the changing dynamics of the process. Now that we have defined our class of systems, we can look at how LEMPC can be used on a nonlinear system whose dynamics change with time. The LEMPC formulation here uses the subscript q to indicate the change in the dynamics of the empirical model to emulate the dynamics of the real process. The economic cost function is given by the first equation, which is subject to the constraints defined by the empirical model, the state and the input constraints, and finally the Lyapunov constraints highlighted in red and blue. LEMPC is a two-mode advanced control strategy. In this slide, we look at the mode 1 operation of LEMPC. A Lyapunov-based explicit stabilizing controller HNLQ is used to design the stability constraints. LEMPC may operate the system in a time-varying fashion while maintaining the predicted state trajectory in the region omega rho hat EQ, which is a subset of omega rho hat Q, thus guaranteeing closed-loop stability in the region omega rho hat Q. The Lyapunov-based explicit stabilizing controller HNLQ is designed to ensure state and input constraints are met. The closed-loop stability and feasibility results hold even in the presence of disturbances due to the properties of HNLQ and the constraint design. The Mode 2 control action of LEMPC ensures that the computed Lyapunov-based explicit stabilizing controller HNLQ decreases the value of the Lyapunov function. If applied consistently, this constraint could drive the state to a neighborhood of the steady state equilibrium point, thus maintaining the feasibility and stability requirements of the system. Now that we have discussed the original formulation of LEMPC, we look at a case where numerical error is introduced to the control system. A truncated Taylor series approximation of the solution to a nonlinear process with the same characteristics as described in the class of systems and under the control action of LEMPC is used to demonstrate the handling of numerical errors. The Taylor series truncation error is used to derive the relationship between truncation error and closed-loop stability conditions. The closed-loop state is maintained within a safe region using the LEMPC formulation. In order to illustrate this, We use an example of a standard CSTR with a general second order exothermic irreversible reaction A gives B, whose state equations are listed here. The control objective is to regulate the process in an economically optimal time varying fashion while maintaining closed loop stability. The economic cost is to maximize the conversion of species A. The manipulated inputs are Ca0 and Q, and the process model is assumed to be input affine. The Lyapunov-based controller is determined using Sontag's formula. The plots compare the states of the system under LEMPC with a truncated Taylor series solution against an explicit Euler. A good agreement between the state predictions leads to closed-loop stability in both cases. Closed-loop state is maintained within omega rho in both cases. The changes in the underlying process dynamics may warrant an online model update. The closed-loop stability and feasibility guarantees rely on the accuracy of the empirical model, and the closed-loop state may leave the stability region omega rho hat q if there is a significant plant model mismatch. LAMPC is designed to maintain the closed loop state in omega rho hat q, which is a subset of omega rho hat safe q. However, if and when the closed loop state x of tk leaves omega rho hat q due to a change in the process dynamics, the LAMPC ensures that there is a certain amount of time before the state leaves the region omega rho hat safe q. The system is operated under LAMPC until the state x of tk leaves the region omega rho hat q due to a change in the process dynamics. The backup control action given by HNLQ based on the last model of the real process is implemented while data is collected to update the model. Once enough data is collected, the backup controller HNLQ and the stability region omega rho hat q are both updated to HNLQ plus 1 and omega rho hat q plus 1 respectively. The controller HNLQ plus 1 is switched if the state x doesn't enter the new region omega rho hat q plus 1 after the model update. If, however, the state x enters the region, then we switch back to LAMPC control action. To summarize, the closed loop stability and feasibility guarantees imply that the state will remain in the region omega rho hat q under normal operation. When the plant model mismatch crosses a certain threshold, the state will leave the region omega rho hat q but not omega rho hat safe q, and a backup control action is implemented based on the last known model of the process. The state will return to the region omega rho hat q plus 1 under the updated stabilizing control action of HNL q plus 1 when sufficient data is collected. In such a case, we switch back to the LAMPC control action. Now, we move on to discussing the robustness of a system fed with false sensor measurements. Traditionally, sensor noise has been considered in robustness concerns. This has been extended to cyber attacks on sensors without trying to differentiate between attacks and changes in the underlying dynamics of the system. Formulations were developed to attempt to detect an attack or model change via the difference between a state prediction and a state measurement, or by the closed loop state leaving a predefined region omega rho hat q. A two-stage detection strategy was consequently developed based on state predictions to prevent the closed loop state from leaving the region omega rho hat safe Q before a certain amount of time passes. If the closed loop state leaves the region omega rho hat Q or an initial detection threshold is reached, the detection threshold is reset and data is collected to re identify the model. This detection method allows for ambiguity in whether the first threshold breach is due to an attack or a model change, and closed loop state is maintained within the omega rho hat safe queue for at least one sampling period for either an undetected attack or a model change. To conclude, a key challenge in optimization based materials design is the formulation of a general material selection problem that is robust to modeling error. Robustness has been a concern in a variety of optimization based contexts in process systems engineering in different ways, a few of which were covered in this talk. Robustness in the optimization based control framework, where closed loop stability guarantees are made under control actions determined from predictions with an inaccurate process model. Second, safety guarantees for LEMPC with an explicit characterization of numerical error. And finally, guaranteed detection and handling of changes to the dynamics of a system. Finally, I would like to take this opportunity to thank the Air Force Office of Scientific Research, the National Science Foundation, and Wayne State University for their financial support in this work.